related rates. First of all, what does this mean? It's a very easy concept. Okay, so what does, first of all, when we talk about rates, what do we talk about? Forget about related. When we talk about rates, so far in this class, when we said the rate of this, the rate of that, what did we refer to? What was the reference? What did we calculate? What was the big deal with the rates? What do we calculate? We're given the distance function. We want to calculate the rate of change of distance with respect to time. What do we do?
Usually the derivative.
Absolutely. Thank you very much. That's what we mean. We mean the derivative, the first derivative, maybe the second derivative if it's the rate of the change of velocity and so on and so forth, but definitely derivatives. Thank you very much. Okay. Now, what does this have to do with rates? Here's the explanation. Let's suppose we have the volume of a cone. The volume of a cone formula is 1/3 pi r squared h. So it's the volume of a cylinder with 1/3 in front. Area of the base times the height with 1/3 in front. Fine. So here's a cone. Here's the radius. Here's the height. Let's suppose somehow I change the rate, or I increase, not the rate, the radius. I increase r. Maybe I stretch it. Maybe it's stretchable or stretchy. So I increase r. What will happen? Well, h must increase. The volume must increase. So if I change or I increase or diminish or minimize the radius, then the height will change and the volume of the cone will change. Another example, we're going to come back to it. So the sphere. This is pi. The volume of a sphere is pi r cubed, pi over 3, 4/3 pi r to the third power. Okay, so let's say I have a balloon and I pump air in it, or I take air out of it. So the volume is this. Let's say it's in the form of a sphere. The radius is this, the surface area. But once I pump air in it, everything changes. The volume changes, the radius changes, the surface area changes. So that's what this means. See, these are functions. This is a function of time. This is a function of time. This is a function of time. How come? If I make changes to them, they all become functions of time. So this is a function of time, function of time, function of time. Which means these three functions are related by this equation. In this equation, I have the volume, the radius, and the height. Their derivatives, their rates, will be also related. They will be found in another equation. That's all it means. So when we say related rates, we obviously start with an equation in which we have whatever number of variables. And when we differentiate both sides, as we did implicitly last time, we're going to get a new equation that relates their derivatives. So I'm going to start with the volume of a cone. So the volume of a cone, 1/3 pi r squared h. Let's say we pump air into, maybe we have a balloon that is in the form of a cone, and we pump air in it. So the volume changes, the radius changes, the height changes. So then when we differentiate both sides, remember, v is a function of time. R is another function of time. And h is another function of time. I'm going to call it t of time. So careful. When I differentiate v, exactly like last time, I get dv over dt. 1/3 or pi over 3 stay outside. This is a constant. But this is a product now. It's a product of two functions of time. So when I differentiate r squared, I get 2r times dr over dt, because that's a function of time, multiplied by the height. This is in the way. Plus, I copy r squared, but now I differentiate the second function, dh over dt. I just give an example. We're going to look at simpler situations. I just give an example in which if we make any changes to any of these functions, then everything changes. If I change the volume, then a change is triggered in the radius and one is triggered in the height. So this is the original equation with functions of time. When I differentiate both sides, I get a new equation that includes their derivatives and the functions, but it's an equation that involves their derivatives. That's what is the meaning of related rates. Yes. Okay, so this is the idea. We're going to look at examples right now. You choose, I choose. Just to illustrate, I meant 364. Okay. Okay, I'm going to start with 21, and then we can choose from here whatever you want from here, anything. But I like to start with 21 because it's related to what I just talked about. And then you can choose anything else. So let's read 21. So this is 21 on page 364. A circle is shrinking, losing 15 centimeters squared of area per minute. So 15 centimeters squared per minute. 15 centimeters squared per minute. What do you think this is? Before we even read on, before we discuss anything. What do you think this is? So we are talking about the area. You either call it A or you call it surface, it doesn't matter. What do you think we're given here? Before you say anything, look at the measurement unit and look at the measurement unit. It must be a derivative because there are two measurement units. It's a rate of change. So what do you think I should write on the left-hand side? It's okay if you're wrong. Just say something. You can use A or you can use S. Let's use area. So what do you think this is? And look at what I just did here. And you'll figure it out in a blink. We are given 15 squared centimeters per minute. So what do you think?
Area cubed.
Say it again.
Area cubed.
So this is the derivative of area with respect to time. the derivative of area with respect to time. Exactly what I wrote here. But it was for volume, dv over dt. So we are given 15 centimeters squared per minute. It cannot mean anything else but the derivative of area with respect to time. Is this okay so far? Anyone? Okay. Find the rate at which the radius is changing at the moment when the radius is 7 centimeters. Find the rate at which the radius is changing when happens. What do you think we're asked to find? Let's read it again. Find the rate at which the radius is changing at the moment when the radius is such and such. What am I asked to find? Yes. The rate of change of radius. How do I write the rate of change of radius? I have the rate of change of area with respect to time. But I want to find the rate of change of radius, of course, with respect to time.
dr over dt.
Of course, that's exactly what I am asked to define. Good. The function is not given to us, but we know what the function is, which is pi r squared. The area of a circle is pi r squared. What do you think we need to do to both sides so that we eventually get to this and we get to this? What should I do to both sides?
Differentiate implicitly.
Very good. Awesome. Knowing that both are functions of time. I put a dot underneath so you understand that these are not variables. These are functions of time. So what do we write on the left-hand side? What do we write on the left? Anyone, please?
dA over dt.
Excellent. Equals. Please differentiate this as a function of time. How do I differentiate pi r squared? As a function of time.
Two times pi r times dA over dt.
Excellent. 2 pi r, 2 minus 1, power 1, times the inner function prime. Excellent. This is what I'm after, which means I have to solve for dr over dt. This is my variable. So can anyone tell us what to write? Remember, we cannot separate these two. So dr over dt equals, I'm solving, this is my variable. What do I need to do to both sides to solve for this?
You just divide by the 2 pi r.
That's it. Keep the dA over dt as is and divide by 2 pi r. This is it. All I have to do is now I'm evaluating when r is 7. dA over dt is given to us. It's right here at the top, 15. 2 pi are numbers and r is given to us as 7. So if we want to approximate, and please let's identify the measurement unit. Can anyone give us? It's a tornado. It's a tornado warning.
Warning in this area until 7:45 p.m. Eastern Daylight Saving Time.
Okay.
Take shelter now in a basement or an interior room on the lowest floor of a sturdy building. If you are outdoors, in a mobile home, or in a vehicle, move to the closest substantial shelter and protect yourself from flying debris. Check media.
Okay. So, if we want to approximate, what would be the measurement unit? Can anyone give us the measurement unit?
Would it be the same as up there, centimeters squared per minute?
It cannot be because this is distance. You are close.
Or no, not squared, just regular
Exactly.
centimeters per minute.
Exactly. Excellent. Excellent. Good. So now, if I lose power, apparently I am in the tornado area. Maybe you are too. I'm not sure. You heard what my phone said. If I lose power, I'll try to come back. Hopefully we don't lose power. We'll see. Okay, so clear. So we have 15. Be very careful how you put this in. You have to put parentheses around the denominator. So it's 2, and it's pi. And it's 7 times 7, and close. So enter it with parentheses around the denominator. If you do not enter parentheses around the denominator, you're not going to get the correct answer. There is another possibility. You can do 15 divided by 2 divided by pi divided by 7. Now this will give us the same answer. That is correct. But if you forget to put parentheses or you don't do division, 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 then you're not going to get the correct answer. So it changes. Now, we have to be careful because it said the circle is shrinking, which means when we talk about shrinking, we have to put a negative sign in here because it's shrinking. So this is negative, and obviously this will be negative. So if the area of the circle is getting smaller and smaller every minute by 15 centimeters squared, then the radius at the same time, the radius is getting smaller and smaller every minute by 0.34 centimeters. So again, this is the equation that relates the area to the radius. This is the equation of the related rates. This is the equation in which we have the derivatives of those functions, not the function. It happens the functions itself, but as well. But this is the equation that relates the functions to each other, and this is the equation that comes from here, and it relates. In other words, it has in the equation the derivatives and whatever else. That's what we call related rates, because the functions are related. They find themselves in an equation. The derivatives will find themselves in a different equation. Okay, so now this is the whole concept. Now we'll practice whatever you want. Now in 22, the circle is growing, which means the dA over dt, the radius is increasing, which means it's positive. If it says shrinking, then the rate of change is negative. If it says it's growing, then it's positive. Okay. So again, as I said, everything the same. Let's choose from here anything you want, or we can work on another word problem.
We do
Yes.
19 there.
Yes, of course. Very good. Let's work on 19. 19. We have a squared equals b squared plus c squared. They're all greater than or equal to 0. They're asking us to find dA over dt, and they're giving us the information. A at that moment is 13, B at that moment is 12, dB over dt is 3, and dA over I'm copying from something else. So B equals 12, dB over dt is 0.25. And then dC over dt is 2. Okay, I'm checking now if I copied everything correctly. So A is 13, B is 12, yes, dB over dt 0.25, and dC over dt equals 2. Excellent. Good. We don't have any measurement units. This is an abstract situation.